We are going to look at the condenser again, but this case we're looking at the condenser as a heat exchanger. And I'm looking at two scenarios. The initial scenario we talked about, which was the condenser as a heat rejecting device. In that particular case, we only worry about the steam exiting the turbine, getting condensed, and ended up with state 1. The control volume that we worry about is the hot steam only. The governing equation we have for that, which we cover in the first part of the video, is H1 minus H7, and the heat rejection rate is m dot, which let's go ahead and get it again. H1 minus H7. This portion we talked about. When we look at the condenser as an exchanger, we are now looking at the control volume that include both the hot steam and the cooling water. Let me go ahead and just circle the comparison of the two control volumes so that you can compare. The pink is the exchanger portion of the control volume. The green is the heat rejection portion only. Okay? So we have cooling water coming in at 17 degrees C, leaving at 30 degrees C. If I were to look at the first law for this pink control volume, looking at my steady state, steady flow, I, first law, as before, we can drop my potential and kinetic energy. There's no work. I am going to be assuming my pink control volume is very, very well insulated. Thus, that is equal to 0. Therefore, this is my governing equation. Or in other words, my entering enthalpies and my exiting enthalpies must be the same. Okay? If you're still confused about what is the relationship between the Qs, that will become apparent in a couple more minutes. Let's just hang on. So let's go ahead and pop in our numbers. Take a look at the pink control volume. There are two exiting streams. Mass of the cooling water, which we're going to call MC, m dot C, with enthalpy at 30 degrees C, and m dot 1, H1. And what's coming in? The cooling water at 17 degrees C plus m dot 7, H7. We know from before m dot 1 equal to m dot 7. Actually, you can look at it from the table, which are both equal to 1 minus y. And I will be collecting the similar terms with the same mass flow rate. So the two terms with the triangle will be collected to one side, the two terms with the crosses will be collected to the other side. And watch. So as I collect my mass flow rate, m dot C H 17 degree C to 30 degrees C. We know m dot for 1 and 7 is 1 minus y, right? Do you notice something? That happens to be the same as that, right? Keep that in mind. What happened to the right-hand side? M dot C. We know the cooling water is liquid water. We can approximate the change of enthalpy of liquid water as its heat capacity multiplied by delta T. In this case, the heat capacity for cooling water is given as 4.18. So, 4.18, delta C is between 17 and 30 degrees C. Oh, we don't need a degree C, just 30. And with this, we know the value of y from prior recordings. We know the values of H1 and HC. You can solve for the one unknown. But what is the significance of why is it that my left-hand side of this first law for the exchanger happen to be the same as the heat rejected by the steam? If you really think about it, that really makes sense. What we're saying here is that the amount of heat rejected by the exchanger is going to be absorbed by whom? By the cooling water. The question we're asking is, why did the cooling water's temperature go up by 13 degrees? And the answer to that is because it has absorbed the heat from the steam being rejected to it. So you ask, where did the heat go? It went there. If we were to write it in the mathematical formula, what can we say? We can then say the following. In addition to the first law, that, I'm going to erase this. For an exchanger, yes, if we look at the exchanger control volume as a whole, the total enthalpies leaving and coming into the exchangers must be the same. And one more equation that will be interesting is that the amount of heat exchanged between the hot and the cold fluids must equal to each other. In our case, the cold fluid is represented by the cooling water, and the hot is the heat rejected by the condenser. From our governing equations point of view, this is your Q hot, and this is your Q cold. Okay?